Okay, we are talking about implicit differentiation in this video. So implicit differentiation is just a way to take a derivative of an equation that isn't solved for y. So it doesn't start with y equals and then everything on the other side of the equals is an x. It doesn't look like this. Typically they're conic sections or other various equations for relations that may or may not be functions. So what we're going to do is we're going to take the derivative of each term with respect to x. And so basically we're going to do d dx of each term. And what we need to remember is we've got lots of chain rule, lots of product rule, and some quotient rule where necessary. So we're just going to go through and take the derivative of each term individually with respect to x. So for this example, we start with y to the fourth plus xy equals x cubed minus x plus 2. I cannot solve this equation for y. It's just not possible. I can't solve this equation for x either. So the only way I can find my derivative is to leave it as it is and take the derivative of each piece. So I'm going to start by taking the derivative of y to the fourth. Now I'm taking the derivative with respect to x, which means when I take the derivative of y to the fourth, I get 4y cubed, and then y is now like an inside function. I would need to multiply by whatever the derivative of y is with respect to x. Now, I don't know what y is because I can't get y by itself. So that's the only way I can represent that I would need to multiply by the derivative of my inside, so to speak, which would be dy dx. Moving on to the next term, I now have a product rule. So I'm going to do a product rule with this term. So for my product rule, I have y times the derivative of x with respect to x. Now that really is just a 1 and we all know that it's a 1. I like to write it in when I'm doing implicit differentiation so that I can just quickly look at each term because it should have a d dx in it somewhere, and this way I know I've taken the derivative of my inside each time. So I have y times dx dx plus x times the derivative of y, which I don't know, it's just dy dx. Moving on, I now have d dx of x cubed. So this one is going to be 3x squared times dx dx. And again, you don't need to write the dx dx. I like to write it just so I can glance and see I've taken a derivative. Next, I have the derivative of x, which is just dx dx. And then I have plus the derivative of 2, which is still a constant. The derivative of a constant is still 0. So I have this thing. Once I get here, the next step I like to do is replace my dx dx with 1. So I'm just going to rewrite just doing that. So I have 4y cubed dy dx, and actually I'm going to write all my dy dx's in a different color just to make it easier. Dy dx plus y plus x dy dx equals 3x squared minus 1. So what I need to do is I need to actually find dy dx. You see, that's what I'm trying to find, the derivative of y with respect to x. So I'm going to get all my, now I'm going to treat that just like a variable. So I'm going to get all my dy dx's on one side, everything else goes on the other side. So let me rewrite one more time. So I have 4y cubed times dy dx, and I have an x dy dx. I'm going to keep those on the left side of my equal sign, and I'm going to move everything else over. The 3x squared is already there, my minus 1 is already there, my minus y comes over. So at this point, again, I'm trying to get dy dx by itself, so I need to actually factor it out just like a GCF. So I have a dy dx that I'm factoring out, and what I have left on the left side of my equal sign is 4y cubed plus x. Now, when I have implicit differentiation, I could have x's and y's all mixed up even when I solve for dy dx, and that's what's going to happen in this one, which is absolutely fine. So to get dy dx all the way by itself now, I need to divide both sides by 4y cubed plus x. And then all I need to do is write what dy dx is now. So dy dx is the 3x squared minus 1 minus y all over 4y cubed plus x. And this is my derivative of that relation. This would give me the slope of the tangent line at any point. And when I have a point, I really actually have to get the x value and the y value to evaluate the slope of the tangent line at any point, which is fine because if I'm only given an x, I could plug it into the equation I have above and solve for y. Once I have numbers in for x, I could probably do that, hopefully. And if not, I will be given the x value and the y value. So we have one more that we're going to do. So we are going to find dy dx at the point pi over 4 comma pi over 4 on the curve square root of 2 cosine x plus y equals cosine x minus cosine y. Okay, let's get started. So what I'm going to do is I'm going to find dx of each term. The first term is the square root of 2 cosine of x plus y. And then I'm going to take the derivative with respect to x of cosine of x minus the dx of cosine of y. So derivative with respect to x of cosine y. Let's go ahead and get started. So in this first one, I have a chain rule, an inside-outside rule, and I have a constant out front. So my constant's going to stay, square root of 2. Then I move into the cosine. The derivative of cosine is negative sine of the same thing times the derivative of the inside. The derivative of x is dx dx, and the derivative of y is dy dx. So that's the derivative of that first term. Again, the constant came down. The derivative of cosine is negative sine of x plus y times the derivative of the inside, which is dx dx plus dy dx. Moving on, I now have the derivative of cosine of x. The derivative of cosine is negative sine of x, and again I need to multiply by the derivative of the inside, dx dx. That one doesn't have to be written down. I find it helpful. Minus the derivative with respect to x of cosine y, which is a negative sine of y, times the derivative of the inside, which is dy dx. So I'm going to go ahead now and simplify anything I can, move my negatives somewhere helpful, and change my dx dx into a 1 each time. So my first term, negative square root of 2 sine of x plus y times 1 plus, I'm going to write my dy dx in red because I want to highlight those, is equal to negative sine of x plus sine of y times dy dx. Now, again, I'm trying to get dy dx by itself. So the first thing that I actually have to do is distribute in this very first term. I need to distribute my negative square root of 2 sine of x plus y to both of these. Then I can get my dy dx's on one side and get them by themselves. So I'm going to go ahead and do that now. So I have negative square root of 2 sine of x plus y times 1. And then I have negative square root of 2 sine of x plus y times dy dx. And the other side of the equal sign can stay exactly as it is. So at this point I can see clearly now, the rain is gone. I'm sorry. So I can clearly see now that I can get my dy dx's on the same side. And actually what I'm going to do is I'm going to move this one. I'm going to add it to the other side so that I'm dealing more with positive numbers. So negative square root of 2 times the sine of x plus y. I'm also going to take this sine of x that I have over here, and I'm going to add it to the other side. And on this side, I end up with sine of y times dy dx. And I also have my plus square root of 2 sine of x plus y dy dx. From here, I need to factor out my dy dx so that I can then divide both sides by it. So factor by GCF, my dy dx comes out. I'm left with sine of y plus square root of 2 times sine of x plus y. I need another. And now I need to divide both sides by my sine of y plus square root of 2 sine of x plus y. And that is my dy dx. So, I have an expression now for my dy dx. Now, that wasn't the only thing that I needed to do. Once I got my expression, I actually wanted to find the dy dx at the point pi over 4 comma pi over 4. So at this point, I need to do some substitution, and I know that the point that I'm substituting is pi over 4 for my x values and pi over 4 for my y values. And I'm going to use different colors just so you can see that I'm actually plugging in two different numbers. Just so happens I'm using the same values here. So I have negative square root of 2 times the sine of pi over 4. And I'm going to add that to pi over 4, x plus y. And then I have plus sine of pi over 4. And this is all over sine of pi over 4 plus square root of 2 times sine of pi over 4 plus pi over 4. And this is dy dx, and it's dy dx at pi over 4 comma pi over 4. So this is how I can write that I'm finding the derivative at a point. You put this line after it, a large line, and at the bottom of the line you put the point where you're evaluating. So let's simplify this some more. Negative square root of 2 times the sine of pi over 4 plus pi over 4 is 2 pi over 4. And 2 pi over 4 is really just pi over 2. And on the bottom, we have a sine of pi over 4 plus square root of 2 times the sine of pi over 2. So let's go ahead. I'm just going to put a little equal sign here and continue on. The sine of pi over 2 is one that we should know. Hopefully we do. It's not one you should use your calculator for. And the sine of pi over 2 is just 1. The sine of pi over 4 is one that we should know. Most people do actually remember that one because that one's square root of 2 over 2. In the denominator, I have sine of pi over 4, which is square root of 2 over 2, plus the square root of 2 times 1. So now I've done my trig, I've done my derivative, and all I have left to do some algebra. However, this is a bit of algebra 2, I would say, as opposed to algebra 1. So let's go ahead, and I'm going to simplify this in what I think will be an easy way. I'm going to simplify it by factoring out the GCF. This has a square root of 2, and this has a square root of 2. So I'm going to go ahead and pull a square root of 2 out. And when I pull a square root of 2 out on the top, I'm left with negative 1 plus 1/2. And I can deal with negative 1 plus 1/2. That's not a problem. So let's look at the denominator. Again, I have a GCF here of a square root of 2. I like that. I have a square root of 2 on the top. I have a square root of 2 on the bottom. And on the denominator, I have, once I factor out my square root of 2, I have a 1/2 plus 1. If you didn't follow that, pause the video, take a moment, figure out what I did. It was just factoring by GCF, and that's something we should be able to do, okay? But make sure you understand where it came from. Now, the square root of 2 over square root of 2 is a silly version of the number 1, and I don't have to write that I'm multiplying by a 1. On the top, I have negative 1 plus 1 half. That's a negative 1 half. On the bottom, I have 1 half plus 1, which is 3 halves, and that's the same as negative 1 half times 2 over 3. Flip and multiply, and I have negative 1/3, I believe. So that is our derivative, sorry, our dy dx of that relation at the point pi over 4, comma, pi over 4. So again, bring any questions you have to class, and I hope you have a nice evening.